So welcome back to the session. Our next speaker is Dr. Indrani Coondoo. She is from CICECO, University of Aveiro, Portugal. Her talk is on magnetoelectric coupling studies in lead-free multiferroic ceramic composites. Dr. Indrani Coondoo is a doctoral researcher at University of Aveiro. She has a very good experience in magnetoelectric couplings studies, and she will now deliver her lecture in the talk.
Thank you very much, Dr. Suresh. At the outset, I would like to mention that I am privileged and thankful to be invited as a speaker at this 5th International Conference on Nanomaterial Science and Mechanical Engineering. So, a very good afternoon to all of you. I am Indrani Coondoo, a researcher working in the Department of Physics at University of Aveiro, Portugal. My talk is on magnetoelectric coupling studies in lead-free multiferroic ceramic composites. I will start with a general introduction, then move on to the detailed results obtained for the prepared multiferroic ceramic composites, and finally end with concluding remarks. So what are multiferroics or magnetoelectrics? So first we must try to understand what are ferroics. A ferroic is a material that adopts a spontaneous internal alignment that can be switched by its conjugate field. Like in ferromagnets, it is the alignment of electron spin that leads to magnetization, and it can be switched by its conjugate field, that's the magnetic field. In ferroelectrics, it is the spontaneous alignment of electric dipole moment that leads to polarization, which can be switched by its conjugate field, that's the electric field. And in ferroelastics, it is the spontaneous deformation or the strain alignment that can be switched by a stress field. So, and of course, there is another ferroic ordering called the ferrotoroids, but it is less established than the other primary ferroic orders, which are the ferroelectrics, ferromagnets, and the ferroelastics. So therefore, multiferroics, as the name suggests, are those materials that combine two or more of the primary ferroic order parameters simultaneously in the same phase. However, according to the current convention, the definition of multiferroics, it also includes other ferroic orderings like not only ferromagnetism, but also antiferromagnetism as well as ferrimagnetism. And moreover, not only single phase, but also the multi-phase materials are also included in the definition of multiferroics. One of the most appealing aspects of multiferroics is the coupling between these order parameters. For example, coupling between magnetic and electric polarization leads to the magnetoelectric effect that refers to the induction of magnetization by electric field or the induction of polarization by the magnetic field. So here we need to see that if suppose I have simply a ferromagnet, then the magnetic field controls the magnetization. And if I simply have a ferroelectric, it's the electric field that controls the polarization. But when we have a multiferroic that couples the ferroelectricity and the ferromagnetism, then the magnetic field can control polarization and the electric field can control the magnetization. So this is the beauty of magnetoelectric multiferroics. Of course, we need to differentiate between a magnetoelectric and a multiferroic because all the magnetoelectric materials, they can have both magnetic polarizability as well as electrical polarizability, but not necessarily, they shouldn't be ferromagnet or ferroelectric. So basically, all magnetoelectric materials are not ferroelectric, multiferroic. Borosites were probably the first known multiferroic materials. In fact, a variety of borosite phases were realized to be either ferroelastic or ferromagnet or ferroelectrics. And the first ferromagnetic ferroelectric single crystalline material was the nickel iodine borosite, which was discovered in 1964. So the history of magnetoelectric effect, it dates back to the year 1894 when Pierre Curie presented through symmetry arguments that an electric field should induce a magnetization and a magnetic field should induce an electric polarization in certain classes of materials. Later, after almost 60 years, a very short remark on linear magnetoelectric coupling, it appeared in this classic book, Electrodynamics of Continuous Media, by Landau and Lifshitz in 1958. In fact, the authors had ended the remark on a rather discouraging statement because the magnetoelectric phenomena had not been observed in any material until then. However, soon after in 1959, Igor Dzhaloshinsky theoretically predicted the magnetoelectric effect in chromium oxide. And then in the following year, in 1960, this prediction was experimentally confirmed in chromium oxide, and thus the field of magnetoelectrics was born. However, unfortunately, the field continued to struggle throughout the 20th century due to lack of any interesting developments. It was only at the turn of the 21st century that the first modern magnetoelectric multiferrite material was developed that marked the beginning of the modern era of multiferroics. And soon after, there was a huge surge of publications, and the past decade has witnessed a dramatic progress. From the applications viewpoint, the real interest in multiferroic material, it lies in the mutual control of electric and magnetic properties. They are useful in spintronic devices, in information storage devices, in microelectronic devices that consumes less power. Then multiferroics have shown promise as materials for harvesting energy, especially through the photovoltaic and the photocatalytic processes. They are also useful as magnetic sensors. And recently, a remarkable progress has been made in exploring the magnetoelectric and multiferroic materials for biomedical application areas like for tissue engineering and like in vivo targeted drug delivery. However, despite their very promising prospects, attempts to design single-phase multiferroics proved difficult. There are indeed very few single-phase multiferroics. The reason is that the chemical constraints for ferroelectricity and magnetism are mutually exclusive. Most of the ferroelectric materials are transition metal oxides in which ferroelectricity is driven by the displacive mechanism and is favored by the empty D shells on the transition metal ion. In contrast, magnetism occurs when materials have partially filled d orbitals. So we see that D0ness, that is empty D shell, it favors ferroelectricity, while the partially filled D shells favors magnetism. So this is a contraindication because it is very difficult to fulfill both the conditions simultaneously. And this fundamental understanding of the contraindication between magnetism and ferroelectricity was put forth by Nicolas Spalding in the year 2000. And after this problem was understood, the next question was obvious: how to overcome this contraindication situation? So one of the very sophisticated approach is identify some other alternative mechanism of ferroelectricity which is compatible with magnetic ordering. That is, instead of having the ferroelectricity which should require empty D shells, try to find some other alternative mechanism. So like in the bismuth ferrite compound, the ferroelectricity is driven by the stereochemical activity of the lone pair of electrons on the bismuth ion. So this is the lone pair ferroelectricity. And just for the sake of information, bismuth ferrite thin films were developed in 2003 by Ramamurthy Ramesh's group, and it's the first modern multiferroic material, and it is still the most popular and the most studied multiferroid. In other class of multiferroics, like the hexagonal rare earth manganites, like the holmium and yttrium manganites, the source of ferroelectricity is basically the buckling of the rare earth oxygen plane and tilting of the otherwise rigid manganese oxide bipyramid. This mechanism of ferroelectricity is called the geometric ferroelectricity. In another class of single-phase multiferroics, like the orthorhombic rare earth manganites, for example, the terbium manganites, the ferroelectricity is driven by magnetism. Basically, a non-centrosymmetric magnetic ordering induces polarization in such classes of material. And this kind of ferroelectricity is called the magnetic ferroelectricity or the spin-driven ferroelectricity. Though the polarization value is pretty low in this class of single-phase multiferroics, but they exhibit strong coupling. Here in this list, we see for the single-phase multiferroic compound, we generally see that the majority of the single-phase multiferroic materials have magnetic transition temperature, which is well below room temperature. Therefore, these single-phase materials are multiferroic only below the room temperature. So from practical application, they are not useful. So, and moreover, because of this factor, the room temperature magnetoelectric coupling is also very small. BFO, the bismuth ferrite compound, is basically the only single-phase room temperature multiferroic, since its magnetic transition temperature and the ferroelectric Curie temperature is well above the room temperature. The other approach to overcome this chemical contraindication is engineering two-phase multiferroic composites, that is, combining a magnetostrictive or a magnetic phase with a ferroelectric or a piezoelectric constituent. This composite approach is advantageous in the sense that there are large number of available options for either phase. One can tailor the magnetoelectric response by choosing a suitable piezoelectric and a magnetic compound, like one can choose a ferroelectric compound with large permittivity and a ferromagnetic compound with large permeability. And therefore, when combining these two, we can expect a large magnetoelectric effect. In fact, the magnetoelectric coupling coefficients obtained at room temperature in such composites, it's much, much higher than that observed in single-phase compounds. Now, how does the coupling occur in such composites? In such biphase multiferroic composites, the magnetoelectric coupling is strain mediated. Now, what do we mean by that? When we apply magnetic field, the magnetic phase, it undergoes a magnetostriction. And this strain in the magnetic constituent is then transferred onto the ferroelectric constituent. And this strain in this ferroelectric phase generates voltage or polarization through the piezoelectric effect. So this is basically the direct magnetoelectric effect where the magnetic field induces polarization. On the other hand, in the converse magnetoelectric effect, electric field is applied such that the piezoelectric phase undergoes a strain, it undergoes a deformation, and this strain is transferred onto the magnetic phase and magnetization is induced. And this is the governing relation, that is the electric field is inducing the magnetization. Now, since this coupling is via strain between the interfaces of the two constituents, therefore, an intimate contact between the magnetic and piezoelectric phase must be maintained. So this can be achieved in various connectivity schemes like the 0,3 composites, 2,2 composites, or 1,3 composites. These are the most popular connectivity schemes. In 0,3 particulate composites, basically the particles of one phase, for example, the magnetic phase is embedded into the matrix of the ferroelectric phase. In 2,2, we have the laminates or the multilayers. In 1,3, we have the nanofibers or the nanorods of, say, magnetic phase embedded into the ferroelectric phase. So one can make various such combination of composites. Here I am showing a few examples of the lead-free piezoelectric compounds like the barium titanate, the KNN, or the NBT, sodium bismuth titanate. And these are the few examples of some magnetic or the magnetostrictive phase like the barium hexaferrite, cobalt ferrite, nickel ferrite, some magnetic alloys like the terphenol D and met class. We prepared composites of barium titanate with barium hexaferrite as well as KNN with barium hexaferrite using solid state method and different wet chemical methods like sol-gel, co-precipitation and citrate combustion. But here I will discuss the only specific case of BCZT, which is the modified barium titanate, which has barium, calcium, zirconium titanate, and it's composite with the magnetic nickel zinc ferrite phase. So solid state reaction method was utilized for the fabrication of multiferroic composites, BCZT with nickel zinc ferrite, where BCZT is the piezoelectric phase, while the nickel zinc ferrite is the magnetostrictive phase. BCZT was chosen keeping in mind its very high piezoelectric coefficient, which is around 350 to 400 picocoulomb per Newton. And the ferromagnetic nickel zinc ferrite was chosen for its high magnetostriction coefficient. So BCZT powder and nickel zinc ferrite powder, they were prepared separately using the stoichiometric ratio of their respective metal carbonates and oxides. And then the nickel zinc ferrite powder was added into the BCZT in different weight ratios, 10, 30, 50, 70. And after mixing the two, the powder were pelletized and sintered, and the obtained samples were characterized for their structural properties, microstructural, electrical, magnetic, and magnetoelectric studies. In the X-ray diffraction profiles, two sets of peaks were identified. One set corresponds to the piezoelectric phase, while the other, the ones which I have shown in the boxed dotted box, they correspond to the magnetic nickel zinc ferrite phase. And no impurity phase was detected, which implies that no chemical reaction took place between the constituent phases. And we also see that the intensity of the peaks of the magnetic phase, it keeps on increasing as we keep on increasing the weight fraction of the nickel zinc ferrite. Rietveld refinement of the XRD data was also performed using the two-phase model with the perovskite tetragonal P4MM space group for the piezoelectric BCZT phase, while the cubic spinel FT3 bar M space group for the nickel zinc ferrite. And using this the refined lattice parameters, the tetragonal strain in the piezoelectric phase and the theoretical density of the composites were also estimated. Here we see the backscattered electron images of the polished surfaces of the composites along with the parent nickel zinc ferrite. Scattered pores and pullouts resulting from the polishing are also noticeable. In all the composites, we see regions of light and dark contrasts, and the composition of the respective regions were analyzed by EDS, that is electron diffraction X-ray spectroscopy, which confirmed that the lighter regions, they correspond to the piezoelectric BCZT phase, while the darker ones belong to the magnetic nickel zinc ferrite phase. And further verification was provided by the elemental mapping that identified the barium and the titanium elements in the lighter zone, while the iron and nickel in the darker regions. In the dielectric permittivity curve with temperature, this is the curve for the pure piezoelectric BCZT sample. It exhibits relatively sharp and well-defined dielectric peak at around 100 degrees Celsius. And this corresponds to its Curie temperature, the ferroelectric Curie temperature. And we see that as we keep on adding different weight fraction of nickel zinc ferrite, this peak diminishes. It gradually weakens, and absolutely no peak of the piezoelectric phase is observed at very high concentration of the nickel zinc ferrite. And at 50 weight percentage and beyond, we start to see the dielectric response from the magnetic transition of the magnetic phase. Here we see the variation of the room temperature permittivity and the loss tangent variation with the different weight fraction of nickel zinc ferrite. Quite obviously, because when the piezoelectric phase is decreasing, the permittivity will decrease. And the reason for this increase in the loss tangent with increasing nickel zinc ferrite phase is basically because the magnetic phase is relatively conducting as compared to the piezoelectric phase. Here we see the variation of capacitance, loss tangent, and admittance in the frequency domain. And prior to these measurements, the samples were electrically poled at 3 kilovolts per millimeter for around 30 minutes. So as, of course, because the piezoelectric phase is decreasing, so the capacitance value decreases. But the more interesting observation is this resonance behavior, which was exhibited by capacitance, loss tangent, and the admittance. And these resonant peak values, they lie between 200 to 400 kilohertz. Therefore, these peaks, resonant peaks, they correspond to the electromechanical resonance in the piezoelectric phase. Because if the peaks were observed in gigahertz range, they are the ones that belong to the magnetic phase. So these resonance peaks, they are basically corresponding to the electromechanical resonance in the piezoelectric phase. Bulk ferroelectric and magnetic properties were also investigated. Composites with up to 50 weight percentage of nickel zinc ferrite exhibited the polarization versus electric field hysteresis loop, thereby confirming their ferroelectric nature. And with increasing the weight percentage of the magnetic phase, the saturation polarization decreases and also the coercive field increased. Similarly, the electromechanical coupling factor and the piezoelectric charge coefficient, it showed a decreasing trend with increasing weight fraction of the nickel zinc ferrite magnetic phase. Here we see the magnetic behavior, and the following observations were made. The composites exhibit extremely slim, well-saturated ferromagnetic hysteresis loops, indicating the presence of an ordered magnetic structure in the composites. And the saturation magnetization, it was found to increase systematically with increasing ferrite content. And the composites, here we see that it's the magnified view. The composites showed very small coercivity values, which were in the range 5 to 20 Oersted. And this reveals their soft magnetic nature. As far as the magnetic coercive field is concerned, initially there is a decrease, and a minimum is reached for the 50-50 composite, which means composite which has 50 weight percentage of the piezoelectric phase and 50 weight percentage of the nickel zinc ferrite phase. And beyond this concentration, the magnetic coercive field value again increases, which is basically due to the requirement of higher energy to switch the larger volume fraction of the available magnetic domains. To identify the local ferroelectric and magnetic behavior, the composites were studied using the scanning probe microscopy techniques such as the piezo response force microscopy, PFM, and the magnetic force microscopy, the MFM. Here the probing tool is basically a cantilever with a tip radius of around 20 to 30 nanometer. In PFM, the cantilever scans the surface in contact mode and monitors the local piezoelectric surface deformation, while MFM uses the non-contact two-pass technique. In the first pass, the magnetized tip, it scans the surface, then it is lifted by a predetermined height. In our case, it was 50 nanometer. And in the second pass, the cantilever, the tip, it scans the, it probes the magnetoresponse. So here, as we see, the strong magnetic contrasts were observed in all the composites. And of course, this is attributed to the magnetic nickel zinc ferrite phase in the composite, and it attests the magnetic property at the microscale. It is also observed that as we keep on increasing the weight fraction of nickel zinc ferrite, that is the magnetic phase, the relative area that shows the magnetic contrast, it also increases. In contrast to MFM, if we see the piezo response, of course, the pure BCZT, it showed the strongest piezo response. However, if we see the composites, only the composite with 70 weight percentage of BCZT showed strong piezoelectric, the piezo response. However, it weakened in other composites. And of course, no response was observed in the magnetic sample. And when we compared the MFM images with the PFM, it was revealed that the magnetically active regions do not show any piezoelectric activity and vice versa. So this implies that sharp interface separates the magnetic and the ferroelectric phase, and there is no apparent interdiffusion. Magnetoelectric coupling was studied by recording the electrical response to applied magnetic field, like I showed in one of my previous slides, the direct magnetoelectric effect. So the samples were subjected to a biased magnetic field superimposed with the alternating magnetic field of 1 oersted at 1 kilohertz. And here we see that since polarization is related to electric field by this relation through permittivity, and since electric field is given by voltage upon thickness, so the relation modifies into this relation. And here, this term, inverse of thickness and the magnetic field derivative of voltage, this term is known as the magnetoelectric voltage coefficient, and it is this voltage coefficient which is experimentally measured, and it has the units volts per centimeter oersted. So in magnetoelectric coupling studies, we measure the magnetically induced magnetoelectric voltage. So the measurements were performed in two modes, transverse and longitudinal. In transverse mode, the magnetic field was applied perpendicular to the polarization direction, whereas in the longitudinal mode, the magnetic field was applied parallel to the polarization direction. In both the orientations of the field, the composites, they show similar behavior. That is, first it increased, the response increased, reached a maxima, then decreased, and then finally the values were 0. And when the field was reversed, the response becomes negative, but it traces the same field dependence as in the positive case. And if we compare the two modes, of course, the behavior is same. That is, it increases, decreases, but there is a subtle difference between the two. The thing is that the maximum response, which was observed in the transverse mode, it was higher than the longitudinal mode, though the difference was small. And secondly, the maximum response in the transverse mode was obtained at lower magnetic field values. I think it was around 100 to 200 oersted. Whereas in the longitudinal mode, the maximum in the magnetoelectric response was observed at a higher field. It was around 450 to 1000 oersted. This difference is basically due to the large demagnetization field, which is found in the longitudinal mode. And as far as the dependence on the ferrite content is concerned, it was observed that the value of the magnetoelectric response, it increases significantly with increasing weight fraction of the nickel zinc ferrite, and maximum was obtained for the 50-50 composite, that is with 50 weight percentage of nickel zinc ferrite. While for higher concentration, both in transverse and in longitudinal mode, the response, it decreased drastically. And of course, the pure BCZT sample and the pure magnetic samples did not show any response because they don't have the two phases together. Here we see the variation of the magnetoelectric voltage coefficient as a function of frequency. Of course, it also shows the resonance behavior, and the frequency values were in excellent agreement with those electromechanical resonance that was obtained in the frequency dependence of capacitance and admittance. But the notable observation in this was the substantial enhancement in the coupling response at resonance frequency. Here we take the example of the 50-50 composite. Here we see that there was a huge enhancement in the magnetoelectric response, both in the transverse mode as well as in the longitudinal mode. The value you see, it's around 5.5 volts per centimeter oersted, whereas in the off resonance condition, the maximum was 14.5 millivolt per centimeter oersted. Similarly, huge enhancement was seen in resonance mode in the longitudinal mode, and quite higher than the off resonance condition. And when we compare this magnetoelectric voltage coefficient obtained at the resonance between the transverse and longitudinal, we see that the transverse mode has a higher response than the longitudinal, though the difference is small, which is very similar to the observations that were made in the off resonance condition. So I would conclude by saying that biphase magnetoelectric composites with BCZT and nickel zinc ferrite were successfully formed, and they showed their individual ferroic properties. That is, they showed the bulk ferroelectric property as well as the magnetic behavior, and they also showed the coupling between them. And the maximum magnetoelectric response was observed for the composite, which had 50 weight percentage of nickel zinc ferrite. And when we compare the values with some other composites containing not only lead-free piezoelectric phase, but with some lead-based piezoelectric phase also, our values are pretty much higher. And as a general concluding remark, I would like to state that still we need to discover new room temperature multiferroic, which has robust coupling between the magnetism and ferroelectricity. It still remains the highest priority for the scientific community. And we also need to develop some new mechanism for the magnetoelectric coupling. From the technological point of view, one needs to reduce the voltage required for the ferroelectric and magnetoelectric switching to nearly 100 millivolt, because this will have an immense impact, especially for the ultra low power electronics. And another key requirement is basically to design proper ferroelectric multiferroics with small but stable spontaneous polarization of around 1 to 5 microcoulomb per centimeter square. So this work was supported by FCT Portugal, and I would thankfully acknowledge the experimental contributions from my colleagues and the technical staff in University of Aveiro. And thank you very much to all of you for your kind attention.
Dr. Indrani, it was a very, very nice presentation from you about ferroelectricity, ferromagnetism basics, and with your results up to date. Okay, the participants, do you have any questions to ask to Indrani?
Yes, sir.
Any of the participants?
Yes, sir.
Yeah.
Hello,
yeah.
sir.
Go ahead. Who is that?
Good evening, ma'am.
Good evening.
Ma'am, so for multiferroelectric for effector, so we have both ferromagnetic property and ferroelectric property. We have.
Yes.
Then if we have this property, then we can say that multiferroelectric effect. This is only one.
No, it is not necessary. Suppose I have a multiferroic material and it has the two phases, both the ferromagnetic or the antiferromagnetic and a piezoelectric. Necessarily, it may not show the linear magnetoelectric effect. No, only in those cases which will show the magnetoelectric effect, the coupling, they are only multiferroic.
Okay, man, thank you. And another thing, madam, in your graph, you are saying that the nickel zinc ferrite, when you adding, then peak is decreases. Madam, why this peak make?
What? In which? I didn't get you.
Nickel zinc ferrite, you show in graph, when you add it, then peak in graph peak decreases.
Here we are increasing the magnetic phase. So correspondingly, the piezoelectric phase is decreasing. Like see, 90 BCZT, 90 piezoelectric, and 10 magnetic. 70 piezoelectric, 30 magnetic. So we basically, as we are going in this direction, the piezoelectric phase concentration is decreasing. So obviously, its effect will slowly, gradually weaken. It will be the magnetic phase now that will dominate.
Madam, what you add for that, it is piezoelectric increases and magnetic field decreases. You got me?
I again did not get. No, I didn't get your question. Are you talking about the peak permittivity or what?
Madam, peak is decreases. So what you add actually? What you add, then peak is decreases, piezoelectric increases.
Piezoelectric didn't increase. Piezoelectricity didn't increase. You see, the piezoelectric effect is also falling. I mean, piezoelectricity is not increasing. Basically, I am saying that I have added two powders. One is the piezoelectric BCZT and one powder is the nickel zinc ferrite. So I am preparing a composite where for suppose take this example. 90 weight fraction of piezoelectric phase plus 10 weight fraction of nickel zinc ferrite. Okay, this is a composite. In this one, it is only 70 weight fraction of the piezoelectric phase and 30 weight fraction of nickel zinc. So in this case, the piezoelectric weight fraction is much less as compared to this. In this case, it is 50 weight fraction of piezoelectric and 50 weight fraction of nickel zinc ferrite. So if we compare it with this, the weight fraction of piezoelectric phase is much less if we compare with this. So obviously the response will decrease.
Okay, madam.
Because the weight fraction is decreasing, so you have less volume fraction of the piezoelectric phase. So obviously its effect will keep on decreasing.
Okay, madam. Okay, thank you, madam. Thank you so much. This is nice presentation. Okay. I understand also clearly.
Oh, thank you. Thank you very much. Thank you very much. I really appreciate the encouragement from the chair and the participants. Thank you.
Dr. Indrani, I have few questions for you.
Few questions, okay. Please.
So my basic question is, here you have prepared the composites. Yes, I understood. Yes. It is composite, yes. But why they are not interacting with each other?
They are interacting with, okay, there are separate phases, okay? Yes. They had separate grains and we need complete separate interface, because if there is any kind of chemical reaction between them, then it will be very detrimental to the magnetoelectric response. Because if we don't have a very separate phase, very separate interface between the magnetic and the piezoelectric, then what will happen is, because the magnetic phase is conducting, so if there is some kind of interdiffusion or any interaction between them, conductivity will increase and we will not get any magnetoelectric response. So that is very important, that we prepare composites with separate interfaces.
Okay. So for example, if you have, it is not concerned about the composites. If you have a material of single phase, and is it possible to have it as a transparent material?
As a transparent material?
No.
Yes, of course.
Is it possible to prepare a transparent piezoelectric or transparent ferroelectric or transparent multiferroic material?
Of course, it should be possible, because basically if I take, suppose, that we need to understand that all the barium titanate can be using some sort of mechanism, we can make it transparent. There are some other also which are optically translucent or transparent. But the thing is, we need to take care that what is the ferroelectricity mechanism in them. Because when we talk about the single phase, multiferroic, it is very important that the ferroelectricity and the magnetism should coexist, like I show in my slides, that the ferroelectricity mechanism then becomes very important if you consider the single phase. But of course, if we have the multi-phase, then the problem will be, it will not be transparent, because when you add the ferrite, it will be not transparent. So in single phase, if you want to prepare, then we have to be very careful of what ferroelectricity mechanism we are handling with. Because if we take those ferroelectric compounds which has, the requirement of the displacive, which the ones which show the most popular, the most observable are the ones which show displacive. So if we use that, we don't get a magnetic response at room temperature, but well below room temperature. So from application point of view, it will not be very useful for us. But if suppose, maybe, who knows, in future you may find, or I can find.
Okay, so because there are many techniques which can be used to prepare transparent ceramics. If we can use them, if we can use them for transparency of this kind of material, besides being multiferroic, besides being piezoelectric or ferromagnetic, they could also be used optically.
Yes, of course. And that will be, yes, right.
Yeah, it's a very good mode of application of the materials. And I have one small query. Is there any relation between the band gap and the band gap of a material and the ferroelectricity or ferromagnetism?
Band gap, you mean to say the optical band gap?
Yes, 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 optical band gap.
Yes, yeah, because yes, I think I did have some communication on that part also, the optical band gap. And in BCZT, of course, it was around 3 electron volt. So yeah, probably we can have this optical
that
band
means
gap
if,
also.
if the band gap increases, what happens to the property? Or if it decreases?
That needs a research, because I'm not much aware of that part. Yeah, I'm not aware of that part. That needs research from my end. But thank you for this idea. I think it can be a very good publication type, you know. Yeah, thank you. And I know because you are an expert in optical band gap studies.
No, I'm not an expert in band gap, but optical. Okay, so thank you very much for your interaction with other people and answering our queries. And it was very nice to have your presentation in this conference.